In section 8.2, we are going to look at surface areas here as an application of integration for surfaces of revolution. So let me develop the formula for you here. So recall here that the area of a right circular cone surface area is pi RL, where R is your radius of the base, and then L is the slant height here. So from the apex down to the edge of the cone. So if you cut this off, if you cut the top of the cone off here and remove this top piece, you get something that looks like this. It's called a frustrum, and that has two radii. It's got a radius down here and a radius up here. So let's call that upper radius R1 and the lower radius R2. And then using the surface area formula for a cone, you can show that the surface area for the frustrum, that is the lateral surface area, not including top and bottom, is pi times R1 plus R2 times L. So pi radius times L, but it's the sum of the radii. So how can we apply this? Well, we're going to find a surface of revolution here, and we're going to add up the surface area of our approximating frustrums. So here is our function y equal f of x. We are going to revolve that, in this case, around the x-axis. So we revolve that around the x-axis here. So like this. And we get this thing that looks kind of like a vase that's on its side. Like so. And what we're going to do is we're going to take the interval from A to B, and we are going to partition that interval up into some subintervals here. And so each partition point determines a point on the curve. And that's where we're going to cut the surface area into pieces. So along each cut, we're going to have a circular cross section. And then we get these frustrums. So there's the first one. We add up its surface area. That's going to approximate the piece of surface area here. And then we've got another frustrum right here. And that's going to approximate that slice of surface area. And another frustrum here, right here. That's going to approximate this slice of surface area. And then one last one here. So in general, we're going to cut it up into n frustrums. So let's say we take one of these guys over here. So that's going to be this second frustrum. And we want to know, well, what's that area going to be? Well, these partition points, let's call them xi minus 1 and xi in general. Then what's going to happen is that our first radius here is going to be the function value at xi minus 1. So that's going to be R1. And then our second radius is going to be the function value at xi. So then the surface area, so your surface area of a frustrum, remember, is right here. So then surface area of that frustrum is going to be pi times f at xi minus 1 is our first radius, plus R2 is f at xi. And then times our slant height L here. And L, that slant height, that's, well, actually this piece here, and that's approximating arc length, just like this straight line segment approximates that little piece of arc length. So your L here corresponds to ds, piece of arc length. It approximates a piece of arc length. So what happens in general then is to get our total surface area, we're going to sum up the surface area of the slices. So S sub I is the I slice. And then each one of those surface areas, well, I'm sorry, this is going to be the surface area of the frustrum for the I slice. And then each one of those S sub I's, that's what this is here. Whoops, forgot my L on there. Is going to be pi f of xi minus 1 plus f of xi times L. And then we're going to sum that up over all I. So our L here then is, that length is going to be square root 1 plus f prime at some x value xi star squared times delta x. And our delta x is right here. And this is the arc length formula. Well, the approximation from the arc length formula. So now we're going to take a limit here as delta x goes to 0. So that means more and more slices. So our sum here is going to turn into an integral from a to b. And then we're going to have 2 f of x values times pi. So here's 2 f of x values times pi. So 2 pi f of x. And then in the limit, our f prime of xi squared turns into f prime of x squared, and our delta x into dx. So your f of x here is a y value, so you can write this as 2 pi y ds. So here's your ds, element of arc length. And then here's your y. Okay, well, that's the x integral. That's in terms of x. If we want the y integral, then we're just going to take the f of x and put y in instead. And then our ds here, you can write that in terms of x as 1 plus f prime of x squared dx, or you can write it as 1 plus f prime of y squared dy. So you can remember integrate with respect to either x or y. So this is still ds. Because arc length you can integrate with x or y. So we got two different formulas that we can use depending on which one is easier. We can integrate with respect to x or integrate with respect to y, just like we could with arc length.